Then let's get started on our next unit. As I said, this is on discrete random variables. And so you can think of the variables idea as the same thing I just described a few minutes ago. It's something you can take on multiple values, and in this case we're thinking quantitative values, so multiple different numerical values perhaps. But not necessarily. I guess you can do this with... No, it has to be quantitative. Random simply means we don't know the outcome in advance. That's the best way to describe that, at least at this level. So we cannot predict necessarily which one it will be. We might have a probability that it falls into one case or another, but that's the best we can do. And then this discrete idea means that there's a list of outcomes I can list out. And in this class, that list is going to be finite, so it's going to be a list I could write down, perhaps in a table. But technically, you can have an infinite discrete distribution. It would just have to be like all the counting numbers and things like that. We won't deal with that in this class. I just want to mention that it is possible, so it's still something to think about if you take a higher level course. All right, so we'll talk about what are random variables, and we'll talk about how to calculate some important things related to them, expected value, and variance. And they will be connected to some of the things we've already seen with data sets before, with samples. And then we'll see our first two examples of a specific kind of distribution. So one of the things we're going to be doing in this unit and in the next unit is looking at very specific kinds of distributions that are useful for modeling specific real-world situations. I'm only showing you a few that are in the book. There are others in the book as well. Feel free to look at those at any point you'd like. And be aware that the book is an introductory textbook, so it's not going to cover all of the sample types, or excuse me, all of the distribution types that are out there. There are many others, and they're useful because when we know that a particular random variable should behave following one particular distribution, we get a lot of information about what to expect. And so that's really useful, and in fact, in some cases we can apply statistical methods using an expected distribution to decide, to make a decision about a hypothesis test. And we'll talk about those later on. We will be focusing primarily on hypothesis tests built on the normal distribution, which is what we'll see next week. All right, so that's enough of that. Our first two probability distribution types are the binomial distribution and the Poisson distribution. And I'll talk about what they're used for in each case. But both are easily seen as important ideas, and they're actually not that hard to work with when you know the parameters and the formulas to use. All right, so we already did that. We'll see where we get here. Okay, so a random variable, by definition, we'll call it a quantitative variable whose value depends on chance. So we cannot predict beforehand exactly what to expect. So some examples of a random variable might be, how many heads will I see when I flip a fair coin twice? Right? I could see 0 heads, I could see 1 head, or I could see 2 heads. There's only 3 possibilities there, but I could list those out. They're separate possibilities, and in fact, I can find the probability of each of those outcomes. So that's exactly what we'll be doing here with discrete random variables. Another example, if I looked at a student in this class, how many credit hours is that student currently taking? Again, that's a number, and it will be an integer, right? You can't take a fourth of a credit. So because of that, I could list out all the different possibilities, and if I were to speak to each of you or somehow see your transcripts, then I would know exactly how many credit hours each of you were taking, and that would be something I couldn't necessarily have predicted in advance. So that's a discrete random variable as well. All right, the last one, the average speed of a car traveling on a particular stretch of road. That's again something that I can envision it numerically. I can think about the possibilities that are reasonable, but without collecting information, I would not necessarily know exactly what that speed might be. Okay. So those are all examples of random variables. And a discrete random variable is a random variable whose values can be listed. So of those 3, which one or ones are discrete? What do you think? Doing a quick probability calculation, there's 8 possibilities for your choice here, right? You can choose the first one as discrete or not discrete, the second one as discrete or not discrete, and the third one as discrete or not discrete. So that's 8 total possibilities. You get a 1/8 chance if you answered on all of them.
Coin flip.
Alright, the coin flip. That's certainly discrete. I can list out the possibilities. In fact, I did that a moment ago. There can be 0 heads, 1 head, or 2 heads. That's definitely a discrete random variable. What else? Any others?
I think the credit hours too, right? Because the credit hours are 2, 3, 4.
Yeah. So credit hours are going to be a finite number, and I would hope they're under 21 or so. So even if they're not, it's definitely going to be under, let's say, 150. Theoretically impossible to do that. So I could list out all the possibilities, and I could compute the probability of each by simply collecting how many of you are taking a certain number versus another. Excellent. So those are discrete as well. What about the average speed of a car?
I would say no, because that average speed of a car could be like point dot 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 dot.
Right. So depending upon how many decimal places of accuracy I want, I could go further and further out, and I could always find a number that wasn't somewhere in my list. Another way to think about it is the average speed of a car probably isn't going to be more than, let's say, 120. So between 0 and 120 miles per hour, somewhere in that range, but it literally could be anywhere in that range. Right? There's no way to say that it can't be 71.1283. Right? That's always a possibility, and I can't tell you which one it would be in advance, so it's random, but it's what's called a continuous random variable because it can take any value in a continuum of values, in an interval of values. Great, great. So the first 2 of these are both discrete random variables. Okay. Now, when we talk about random variables, we want to have a way to decide or to assign a probability to each of the values that that variable might take. And sometimes this can be done theoretically through a model. Sometimes this is done by collecting data. But in any way that I want to do that, I can actually list out those probabilities in a table form. And that's usually the most convenient way to do this. So a probability distribution is a listing of the possible values for a discrete random variable with the probability that is associated to each of them. And so usually, and again, this will be written in a tabular form, but for certain types of distributions, we have ways to calculate entries in that table directly, so we might have a different way to represent those functions. These are functions. They're often called probability distribution functions, and so if you have a TI-83 or TI-84, you may notice there's a normal PDF, for instance, is one of the options. It's the probability density function, and it's a probability distribution function itself. Okay. That one is for continuous distribution. So how does it work? Well, if we think about the first example we talked about, flipping a fair coin twice, and then recording how many heads I see. Well, as we said, the possibilities are 0, 1, and 2. And if I wanted to know the probability of each of those, I could list it out as 2 separate choices. And let's say heads and heads. There's a 1/2 chance I get heads, 1/2 chance I get heads again, 1/2 times 1/2 is 1/4. That's where this number came from. 125. Probability of 1 head and 1 tail? Well, it's because it can happen in 2 directions. It can happen heads then tails, or tails then heads. And so because of that, again, there's 2 ways to get that. I get 0.5 is its probability, and then the probability of 2 heads would be tails followed by tails. So again, 1/2 times 1/2, which is 1/4. And a key thing to notice, these probabilities have to add up to 1 overall, because they're covering all of the possibilities together. Down. There we go. All right. Oh, I forgot to mention, when we talk about a random variable, we will often use a capital letter, and the default is X, capital X. So I don't always use that as my initial one, just like capital X is usually the function name that's chosen in an algebra class. Capital X is usually the one chosen as a random variable's name. You should always define it in words before you use it. So in this case, my random variable X is the number of heads in 2 flips of a fair coin. And I can think about lots of different values it can take, or at least 3 values in this case. If capital X is my variable name, lowercase x stands for a single value that it can take. And so then I can look at things like the probability that my random variable takes a specific value. So this is the probability it takes the value 0. This is the probability it takes the value 1. And this is the probability that it takes the value 2. And that's how we'll do that notationally. If I happen to need an extra random variable name, I'll then default to y, capital Y, and then capital Z, and just as with x, the lowercase y and the lowercase z will be specific instances of those. Okay. All right. So what are we going to do with this? Well, how many of you have calculated your grade in a course where the grades are weighted by category? Like exams are, let's say, 30%, and homework is 25%, and so on. When you do that, you take the weight of the category, so like the 25% for homework, you multiply that 0.25 times the average you have on homework, and that's your homework contribution to your overall grade. And then you add to that the contribution you get from exams. If it's 30%, you take 30% of your exam average and add that in. And then when you do this across all of the categories, at the end, when you add all those numbers together, you get a number between 0 and 100, and that's your grade in the course. That is an example of an expected value calculation. Okay? So it's like one in the sense that we would treat the probabilities as the weights of those categories. So the expected value in general is kind of like the random variable equivalent of the average, random variable equivalent of the mean. So what we're doing here is we're looking in the long term and asking, what would I expect to happen on average if I did this random event over and over and over again, and I recorded the value of my variable? What would be my average outcome? Okay. So the notation we use for that is capital E, and then the x is inside of brackets, so this would be the expected value of the random variable x. If it was a different variable, I would say the expected value of the random variable y, and so on. So this is just like function notation. Occasionally, if I have a formula that has to use e of x in it, that can get really tedious to try to read with all the nested parentheses and brackets and so on. And so in that case, we'll use the substitution here. We'll use this letter mu to stand for e of x, and that's the Greek letter that's equivalent to the letter m, mu for mean. We'll be using that same idea later on when we talk about the mean of a population. We use mu in that situation as well. Okay. So if I write the probability that x equals x as little p of x, I think of this as the probability of x, just makes it a little easier to write as a formula, then here's the formula for calculating the expected value. The expected value of x is, does anyone know what this symbol is? Right. It's a Greek letter sigma, the capital sigma, and it stands for a sum. So what it says is I want to add up x times p of x across all the values of my random variable. So I think about all the different values it can take. For each of those values, I take the value times its probability and add those results together. That's a weighted average that stands for the expected value in this case. So let's do that. Let's do it for the coin flip question. If I were to do this over and over and over again, flip a coin twice and record how many heads, what would I expect my average outcome to be? First, I'm going to write down what X stands for, number of heads in 2 flips of a fair coin. So let's reconstruct that table. Let's see, there could be 0 heads, or 1 head, or 2 heads. What's the probability I get 0 heads? Anyone know? Okay. Well, 0 heads would be tails and tails. And if it's a fair coin, there's a 1/2 chance I get tails on the first toss. And there's a 1/2 chance I get tails on the second toss. So it should be 1/4. And I like to write that as decimals in my chart. So that's 25% chance. What about for 1 head, meaning 1 head and 1 tail? We can always reconstruct it if we need. Right, we'll get 1/2 when we're done because heads first, tails second is 1/4. Tails heads is 1/4. And those two things together add up to 1/2. You don't have to write the 0 here, but I'm doing it just to line up the decimal places. And then my last case, I can either calculate it directly or I can realize these things need to add up to 1. I've got 75% already, so the other 25% should be here. I could also calculate it, and I could also think about, in this case, there's so many symmetries that the 0 heads and the 2 heads have to be the same. Because 0 heads is the same as 2 tails, and 2 heads is the same as 0 tails. So if it's a fair coin, all of those probabilities should be equal. Alright, so now to compute the expected value, I need to multiply these things. Well, the first one's pretty easy. 0 times 0.25, that's 0. Second one's not that bad either. 1 times 0.5 is 0.5. 2 times 0.25 is also 0.5. And when I add those things together, I get 1.00. So what this tells me is that my expected value for the number of heads is 1. Now if you take a step back and ignore all of the probability calculations we just did, ask yourself, what would I have expected as the quote-unquote average outcome if I flip a fair coin twice? I would expect the average outcome to be 1 head and 1 tail. Sometimes I'll have 2 heads, sometimes I'll have 2 tails, but because of the symmetries here, I think more often than not I'll be right in the middle. That would have been my argument without using any numerical evidence whatsoever. Using the expected value, I can compute that. I get exactly 1 as my expected number of heads. And so I did put the calculation on the slides just so you have that as a reference going forward. Think of it as a weighted average. You take the number times its probability and then add those add those values together to get the expected value. Okay. And again, in this particular instance, it's easy enough to visualize what's happening. And because of all the symmetries, we'd expect the expected value to be 1. But there are plenty of cases where it's not so easy, and that's where this might be exceptionally useful. You can think about in the long run, what would I expect the outcome of this event to be? And this can help you make decisions in terms of investments, for instance. If you think that I have a certain probability of this outcome, a certain probability of this outcome, a certain probability of this outcome, I can think then from that, what is my expected value each time I invest? And then I can invest my resources appropriately by weighing those expected values to think about what I would expect to get back on average, even if I don't know what will happen in one individual instance. Okay, so just like the expected value is an analog to the average for sets, you can think of the variance as an analog to the variance for sets. Right, so if you remember when we calculated the average, we added up the numbers and divided by the total number of them. Well, that was essentially the same as if we were drawing from that set and assuming each one was equally likely. Then we would be calculating the expected value. If you use the same reasoning, the variance, as we will calculate it for discrete random variables, is the same idea where we are weighting the squared deviations from the mean. So for sets, we added up the squared deviations for the mean and then divided by n for a population variance or by n minus 1 for a sample variance. And in this case, we're doing something very similar. Instead of dividing by n, we're multiplying each entry by its individual probability, the proportion of times we expect it to happen. All right, so that's the big picture idea. So the variance is computed by taking the average squared deviation, and again, in this case, it's a weighted average. And so the variance notation we'll use is capital V of x for variance of x. And occasionally, if I need to use the formula, I'll write sigma squared, just like we use for population variance. Okay, so just like mu is the population mean, sigma squared is the population variance, I'll use the same thing as a shorthand for the variance of a random variable. All right. So how do we compute it? Well, it's going to be very similar to what we did with individual samples. You take an element, subtract the mean, square that result, and then multiply by its probability. Once you've done that, you add all those values together, and that will be the variance. So dissecting this formula, the variance is the sum over all of the values of my variable. The value minus the mean squared times the probability of that particular value. Well, once you have a variance, if you recall from samples, the square root of that was the standard deviation. So we can do the same thing here for random variables. I can take the square root of sigma squared to get sigma, and I take the square root of v of x to represent that value. So if I wanted to know what the standard deviation of a particular event might be, I can look at its variance and take the square root to compute that. All right. So that's a lot of formulas already. Let's compute the variance for the coin flip example. Okay. We'll see another way to do this later today. So let me reproduce my chart. All right.
What did you do, Bella? What? She likes it. Don't let her out of it. Baby, please. Keep her ears open and put them down.
So in order to calculate the variance, I really need to get at this term. And I'm just trying to give intermediate values that make it a little easier to see where it comes from. If you want to write this and these two things in your chart, that's okay. But it will usually be helpful to have these intermediate values to make sure that things line up correctly and you don't make any mistakes. So what was my mean in this case? I'm looking at the number of my expected value. What was it?
Stay back. Stay back. Stay back, Bella. Stay back, Allie and Bella. Okay, I'm going to leave about you.
Right. I could get 0 heads, 1 head, or 2 heads, and the expected value is exactly 1. So everywhere I have this mu, for this problem, I'm putting in a 1. All right, so what is x minus mu here? 0 minus 1 is negative 1. Okay. 1 minus 1 is 0, and 2 minus 1 is positive 1. And you can think of this as relative to the mean. Where is this value? 0 is one value below the mean. 1 is exactly the same as the mean, and 2 is one value above the mean. That's what this deviation column is doing. I want to square those so that I get rid of negative signs, and I also add extra weight to the ones that are far away. So squaring negative 1 gives me a positive 1. Squaring 0 gives me a 0. And squaring 1 gives me a 1. And then lastly, I multiply each of those values times its particular probability. So what would I have? 1 times 0.25, 0 times 0.5, and 1 times 0.25. When I add those things together, 0.50 is what that should be. So my variance is 0.5. You can think of that as the equivalent of the variance in a population if I were to have numerous instances of this. Okay. Let's see if this lines up with my calculations. Indeed it does. And so then what is the standard deviation? I will use this notation. I don't know if that's standard, but I'll also use this as well. And the formula is the square root of the variance. Square root of 1/2, which I guess is square root of 2 over 2. And that's 0.7071. Any of you who've taken trigonometry, you've probably seen the square root of 2 a lot. Square root of 2 over 2 a lot, excuse me. That's this number right here. Alright. So that is the standard deviation for this particular example. Are there questions about expected value or standard deviation thus far? Well, let's do a frequency table example then. So this is one where the function is not quite as simple, and the relative frequency is actually determined from looking at data. So in this case, I have a statistics class with Professor Weiss, who asked 40 students in one of his classes, he has very good classes apparently, to state how many siblings they have. And when you looked at the data he got back from that questionnaire, he found the number of siblings was anywhere from 0 to 4 in the list. And he tabulated how often he got 0, 1, 2, 3, or 4 as a response. So we're going to call the number of siblings the student obtained as capital X, this random variable X. And we're going to find its expected value and its variance. So let me first reconstruct that chart. And what I'm going to do is I'm going to treat the relative frequency as the probability, P of X. So 0, 1, 2, 3, and 4 were the possibilities for a number of siblings. And 8 of the 40, which is exactly 20%, had no siblings. Go 3 decimal places. 17 of the 40, which is 3 decimal places, was 0.425, had 1 sibling. 27.5% had 2 siblings. 7.5% had 3. And, well, 1 person had 4. All right. So the first thing I want to do is to calculate the expected value. And what that's going to be is the sum of each x value times its probability. So that'd be 0, times 0.200 plus 1 times 0.425 plus 2 times 0.275 plus 3 times 0.075 plus 4 times 0.025. Okay. 0.425 plus 0.45. 0.5 is 0. 21, and then 15 at the end. 0.225. And then 4 times that. 25 times. I think that's right. Okay. And when I add it all together, 0.425 and 0.225 should make 0.65. 450 plus 0.1. I think I get 1.2. Oh, I did something wrong here. Alright, let me multiply it out again. Double check. So 1 times 4.25, 2 times 0.275. Yep, there's my mistake. That's a 550, not 450. Instead of 550, and instead of 1.3. And that matches what I have in the slides. So another word of warning, don't do it in your head. Okay. So 1.3 is the expected value. What that means is, if I were to pick a random student in the class and ask how many siblings they had, and I did this over and over and over again, in the long run, I would expect the average response to come out to 1.3. That's what the expected value here tells me. Okay. Well, I also want to calculate the variance. And I'm going to do that by reconstructing the chart again, because I want that whole chart available to me. Now let's see, 0.2, 0.425, 0.275, 0.075, and 0.025. Okay. I want x minus the mean. I want x minus the mean squared. And finally, I want to multiply that times the probability of x and add those results together to get the variance. Alright, so this is going to take a little work. Let's see. X is 0. The mean we just calculated was 1.3. 0 minus 1.3 is negative 1.3. Alright, 1 minus 1.3 is negative 0.3. 2 minus 1.3 is 0.7. 3 minus 1.3 is 1.7. And 4 minus 1.3 is 2.7. In this case, because each of these went up by 1, I can take my first answer and just add 1 each time. And that would be another way to get there. I always like to do it from scratch and then check at the end that those things lined up. It's a way to make sure I didn't make a mistake there. Well, now I want to square these things. Again, I'd recommend using a calculator, but 1.3 squared is 1.69. 0.3 squared is 0.09. 0.7 squared is 0.49. 1.7 squared is 2.89. And 2.7 squared I don't want to do in my head. 7.29. I should have been able to do that anyway. Alright. So now all I need to do is to take this times this here, 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 and add them up. So I'll simply write those down. 1.69 times 0.2 is 0.338. 0.425 times 0.09 is 0.03825. 0.275 times 0.49 is 0.13475. 0.075 times 2.89 is 0.21675. And 0.025 times 7.29 is 0.18225. And now when I add these together, that will give me the variance. Just estimating first, about 5 and about 4. I expect about 0.9 maybe. Let's see what happens. Yeah, how about that? When I add them together, I get 0.90999. Okay. That's essentially 0.91. In fact, if I round any number of decimal places, that's what I'll get. But the variance is 0.91. And then the standard deviation is the square root of that. And I get 0.9539. That's the standard deviation. So we'll see if that lines up with my slide calculated examples. Okay, good. 0.91 is the variance that I get. And I guess I chose not to include the standard deviation there, but that's exactly what it'll be. Alright, any questions about that? When you're calculating a variance with a table like this, I would strongly encourage you to include those extra values, those extra columns, because it's easy to make a mistake here and not see it if you try to go straight to adding up those numbers. If you do it this way, you can usually spot the mistake, and in fact, if you are careful, you can use a spreadsheet program like Excel to do this for you quickly. You can type in the x value, and in the next column you can say equals that number minus and then whatever value you're subtracting. If you pull down, it'll autofill the rest of them with the same formula. And then you can say equals the square of the previous one. Pull down, it'll square them, and then equals this times this. Pull down, and it'll calculate them, and then sum. So it will take you about a fourth as much time to do it in Excel as it will to do this, and it's guaranteed not to make a mistake if you type in the formulas correct. All right. If there are no questions at the moment, it's 10:20. I think we should take a 5-minute break. And then we'll talk about our first specific example of a discrete distribution called the binomial distribution.